to the usual Ginzburg-Landau. So first of all, at the limit, you will not have just this constraint of modulus 1, but also you hope that the divergence constraint goes to the limit. So like this, in fact, you will get to a very rigid equation. So in fact, since you are divergence-free vector fields, then by Poincaré lemma, at least locally on simply connected domains, you know that your vector field is a gradient perp of a stream function, and the modulus 1 goes to this aconal equation. Okay? And for aconal equation, in general, you will think to distance functions to some set, and you see that you will have ridges, so line singularities coming in. So for example, if you take the distance function to the boundary of a rectangle, you see, and you take the gradient perp of this stream function, you see that these are line defects, so they are jumps for your vector field. And okay, and for example, if you take the boundary of a circle, then you will see this kind of vortex coming in. Okay, so the difference with respect to the usual Ginzburg-Landau is that the energy will concentrate on line defects, and in fact, vortices will be zero energy states. Why? Because in the usual Ginzburg-Landau, you don't have this epsilon, okay? So the usual Ginzburg-Landau is like you put in factor epsilon, okay? So you will have just this energy. So there, a vortex will have the cost of log epsilon. So you multiply with epsilon, so that goes to 0. So at the limit, you will not see it anymore. Okay? Okay, so we will treat this model. So now I will go to the physical motivation. Then, okay, we will study the asymptotics when epsilon goes to 0. And in fact, why do we do this? Because, for example, if we want to treat the minimization of this problem under some boundary conditions, it's much easier to look on a reduced model. So that would be a model that will exist on the jump singularities of our configuration. And in fact, in all this theory, we will use entropy method coming from scalar conservation laws. Okay? And at the end, we will study the reduced model and say what are the minimizing configurations. So for example, is that distance function give us the minimal configuration. Okay, so first of all, what's the motivation? Is there a connection with liquid crystals? So first of all, let me recall the Ozin-Frank theory for nematic liquid crystals. So okay, in such an audience, I think I can go quite quickly on this. So okay, we have this container. We have that the director of the rod-like molecule. So this optical axis is considered here with values in S2. So we don't identify here tails and heads of the molecules. And we will consider this elastic energy density. And okay, for the moment it's 3D. And then I will explain why we will look to 2D. So, okay, the aim is to minimize such energy density under some boundary conditions. And okay, at least for the analysts, what is important is that, for example, when all these elastic constants are equal, then we get to minimizing harmonic maps. And there we know, so the theory is already done analytically, that, okay, we will, at least at the minimizing configuration, we will expect to have these vortex point defects. Okay? And, okay, and also in general for different constants, we still know that the minimizing solutions will have defects of dimension less than 1. So if you want to look to defects of dimension 1, then you should look to another model. Okay? And in fact, this is how this line energy Ginzburg-Landau was came out. So we will. So this is a model, at least in mathematics, it's called like the Aviles Giga model. So they looked at the smectic state of a liquid crystal. So we know that at the smectic state, the molecules will tend to align on some parallel parallel interfaces. Okay, so these interfaces can be seen as the level sets of a scalar function, and the director is given by the normal vector to these level sets. Okay. So now the first idea would be to study, as before, the Dirichlet energy of such a function. The problem is that such a configuration is very rigid. It's like the aconal equation. So you cannot treat it like this. So therefore, you have to do a relaxation. And their idea was, okay, we will keep that U is a gradient field. Okay, so U is like gradient phi, and see that here U will be of modulus 1. So, okay, if you rescale here with epsilon, so you will see that at the limit, the gradient of phi will be 1. So U is like here. And here, again, you will have like a regularizing term. Okay, so that was their idea. So, okay, before I said that we work with divergence free, but for example, if you are 2D, divergence free or curl free is the same, right? Because you will just turn by pi over 2 your vector field. Okay, so they ask what's happening, okay, in 3D, in fact, in any dimension, they ask what is the behavior of the minimizer. And so, okay, to know what are the structure of the singularities coming in, and also to treat this rescaled then okay? So in my study, that will be like the section. So it's like considering a cylinder, and then you take a section. So that's why we study the 2D. In fact, in 3D, we don't know almost anything about that. Okay, this model has also another physical motivation that comes from micromagnetics. So here, omega will mean, in fact, the body of a magnetic element. So a magnetic, ferromagnetic material can be described by the magnetic, what is called? Yeah, the magnetization. Okay. The magnetic moments. This is what I want to. So the spins. So the magnetic moments that can be seen as a vector field defined from omega with values in S2. So this is like in liquid crystals the director. Okay. And then this magnetization will minimize an energy that I will consider here by ignoring the external magnetic field. So the first term of the energy is a local term that will give the interaction of at short range interaction between the spins. So of course this term will favor that the magnetization is constant. Then you will have a second term that is the anisotropy of the material. So they will tell you in which direction the magnetization would like to go. So here we will consider planar anisotropies. So the M3 component will be penalized. So therefore, at the end, you would like to be in plane. Okay. And the trickiest part is this stray field energy that is a non-local term that will give you the interaction of long-range interaction between the spins. And this stray field energy will penalize the divergence of the magnetization. So in fact, it's like in electrostatics, the stray field will be a gradient field. And in fact, it is generated by the volume charges that is given by the divergence, and also is generated by the surface charges. Because here, if you look carefully, you will penalize the normal component at the boundary. So for example, here you will see that if you have a constant magnetization, so volume charge is 0, but here, so the normal component is M3, so you have a lot of surface charges, so so this stray field is generated by these surface charges. Okay, so now how do we get the previous model? So again, we will consider that the magnetic element is like a cylinder.
But and this guy is not direct, no symmetry M to minus M, it's a different state. M is unit vector magnetization.
Yeah, right. Here it doesn't matter, so it's not like in liquid crystals, you don't need to, it's not RP2 or something, so it's S2, really S2. Okay. So, so we will consider that the magnetization doesn't depend on the X3 component, so it's like looking to a section. So therefore, we get to a vector field that is defined on a 2D domain with values in S2. And we will consider a regime. Okay, I don't speak a lot about this regime, where in fact we will see such kind of line singularities, which is good for our aim. And in fact, this regime tells us that the stray field energy is strongly penalized. So that will give us, in some sense, the first leading order term of the energy. So this is like considering that we are divergence free. So in fact, I simplify here because, I mean, we treat the model also by playing with the energy generated by this. Okay, but anyway, so if you plug in all these things, then you get to this like Ginzburg-Landau model, so of course divergence free. So what is different with what it was before is that here you have also the Dirichlet energy of M3. Okay, so this is a little bit bigger. And here, see, so M3 squared, you can write it as 1 minus the in-plane components to the squared. Okay, so this is like Ginzburg-Landau, but the potential is like linear. It's not quadratic. Okay. So, okay, this is similar to what we want. Okay, so now let's do some mathematics. So please interrupt me if you have some questions. So again, so let me summarize. We will have a 2D domain. Okay, so now the vector fields are M, like the magnetization everywhere, with values in R2, divergence free. And we will consider this Ginzburg-Landau energy, where we will take here a potential G. You could think as G as a power function. Okay? So power 2 is the usual Ginzburg-Landau. Power 1 will be the previous micromagnetic thing. So an increasing function that vanishes just in 0. Okay, so for example, so here you know that when epsilon goes to 0, then this should be really 0. So M will be with values at the unit circle. Okay, so what is the expectation when we will treat the asymptotics when epsilon goes to 0? So first of all, we want to prove that at the limit we have this aconal-like equation. So therefore, in order to get a rigorous reduced model, it's important this step, so the compactness result. Why? Because see, if you consider here configurations with finite energy, then you will get for free that the modulus will go to 1. But you can have some oscillations there that will tell you that in fact the limit could be 0, right? So therefore, in such a study, the compactness step is very important. And then what is more important is what is the limit energy. So what will happen? It will happen that these limit configurations, so we'll have this kind of line singularities where the magnetization will jump from one state M minus to another state M plus. So the fact that you are with modulus 1, it will tell you that here these traces, so what you will put on one side of your line, will still have modulus 1, and on the other side you will still have a modulus 1, so you are S1. And the fact that you are divergence free, it will tell you that the normal component is continuous, so will not jump here. So in fact, each jump is characterized by a unique angle, theta. Okay? And in fact, so what we'll hope is that in fact this energy will tend to such a line energy that lives just on this jump set of M, and the density depends just on the size of the jump, so just on the angle, and here you will have like a cost function. Okay, so this cost function will go from 0 to 2 because the maximal thing will be the diameter on S1. Okay. So of course the first question is that in the energy you have a potential G, here you have a cost function F. So the first question is what's the relation between the two, right? So so we will make here a 1D ansatz. So in order to get this relation between NFG, so what we will do? So this is what we will have at the limit, okay? So we'll have such a jump. So we will make a zoom along a jump, okay? So this is the zoom. And there we know that at epsilon level, we have to move continuously, okay? So here, you should, so the ansatz is that this transition layer is one-dimensional, okay? So everything will happen in the normal direction to the jump. So the jump is here, okay? So if we make a zoom here, we can consider that the jump is like a line, okay? So, okay, so, so then what do we do? So we will plug in such a 1D transition layer. So since we are divergence free here, it means that the normal component is constant. So everything will happen in the orthogonal component. Then you plug in this transition layer in your energy. So you will have like a 1D energy, and you know that at the minimizing level, this term will equal with this term. So therefore, you have this equality, and then you say, okay, this is the minimal equality that I want to impose at the cost function, okay? So doing this 1D ansatz, it's always, you should have such a relation between f and g. So in particular, if g is a power, so for example, t to the power 2, then f will be power 3, okay? Good. So now, okay, so that was a 1D ansatz. So because in physics in general you make ansatz, but that will give you in general for an energy just an upper bound. In mathematics, what is very important is to get the lower bound in order to have matching, because otherwise you don't get the rigorous reduced model, okay? So, so the good method for that is the gamma convergence. So, so what we want to prove is that our Ginzburg-Landau energy at level epsilon will converge to these line energies. So the first step would be to show that the limit energy is a lower bound, okay? So this gamma convergence is not a convergence point-wise, but rather to, it's adapted to minimizers, okay? So, so first of all is the lower bound, then is the upper bound that will tell you in fact that this lower bound is the best lower bound that you can get, so it's the highest one. And as I said, the goal of this gamma convergence is to say that the minimizers of the Ginzburg-Landau energy will converge to the minimizers of the limit energy. But in order to have that, you need the compactness result, right? And that's why in general this is a step that maybe sometimes it misses. So because that will tell you that you are looking to the right topology when you do this gamma convergence. Okay, so anyway, what is important that once you prove this, then you have the convergence of the minimizers. So instead of looking to this, you will look to an easier problem. Okay. So what will be the technique? So first of all, in order to get the upper bound, you will just plug this 1D ansatz that we did, okay? And then the question is this 1D ansatz the good one? So when you will look to 2D perturbations, do we have that the lower bound, this 2D lower bound, coincides with your 1D energy? And for here, we will use, as I will explain later, the entropy method for the aconal equation.
Excuse me, please. What you call entropy? Sorry for stupid.
Yeah, I will come to this. Just bear me like 5 more minutes, and I will explain to that. Okay, so that was our goal. So you can ask, okay, do you know an example where everything goes well? Okay, so hopefully there are some examples like this. So if you consider exactly that rescaled Ginzburg-Landau energy where the potential is quadratic, okay? So here everything goes well. So first of all, that was quite an achievement. So this compactness result that was due to Ambrosio De Leris Mantegazza, and on the other side another team, De Simone, Kohn, Müller, and Otto. So this team I will always write DKMO. So they really prove that that if you have finite energy configurations that are divergence free, then you can rule out oscillations. So in general, for example, if you don't have this divergence free, then you can have loss of compactness. Okay, so the limit cannot be with values in S1 anymore. Okay, so the compactness is done. But now, this is maybe for specialists, there is a bad news. The bad news is that the limit configuration is not BV. So B meaning that the derivative, so the gradient of this is not a finite Radon measure. Why? Why I say that this is a problem? Because we have in mathematics a theory that tells us that for such a space, we know what is a jump set, right? Because our aim is to define our limit energy. So we really need to have some jump lines, okay? So, okay, this is a bad news, but in fact, okay, you don't need to do just BV, but even in this case, you can prove, and that was done by De Leris and Otto, that finite limiting energies, configurations, do have the same kind of structure as the BV, but there, in fact, the jumps are not bounded in like linear, like in BV, but with power 3. Okay. And why? Because, as I said, if you remember the 1D ansatz before, we said that if G is a power, then what we will have here is a power plus 1. Okay. So this gamma convergence problem was almost done by works of Aviles, Gigagin, and Kohn, and Conti and De Leris. So here we really have such a convergence. I say that is almost done because the upper bound, when you want to do the upper bound, that was done just for BV configurations. So not for the much larger space of configurations which are just cubic in the jump. Okay, so now you should ask, okay, what's happening for general potential G? Okay, so do we have the gamma convergence? So do we have the matching of the lower and upper bounds? Okay? So in general, the answer is no. We don't have such a thing. And then the question is how you will create such a cost function. So the idea is that if you can construct some cost functions f such that such a limit functional cannot be a gamma limit, okay? So we know that the gamma limit should be lower semi-continuous, okay? So if you can find a cost function that will not give you something that is lower semi-continuous, then it's clear that your program cannot go, okay? So now, what does it mean lower semi-continuous? I will give the definition later, but what does it mean? It means that if you have a jump, okay, so you go from here to here, then you cannot create a microstructure that will decrease your energy. Okay. So this is why, for example, Ambrosio de Mantegazza said that, okay, if the cost function is more than cubic, then that will not lead to a lower semi-continuous thing. Okay, so that energy cannot be a gamma limit. So let me explain how is this microstructure, right? So imagine that here you have your jump, and you jump from here to here, okay? So what you will do is that you will make smaller layers, so this eta will go to 0, such that when eta goes to 0, anyway, if you put something here, it will converge to your jump, okay? And the microstructure is what? Is in fact to decompose such a jump of 180 degrees in smaller jumps. So here you will have a jump, here we will have a jump, here we will have a jump, but smaller jumps, but the length of these jumps is maybe big, okay? And the thing is that if the power is bigger than 3, that microstructure will beat in energy, so we have less energy than the direct jump, okay? So that's why you cannot have lower semi-continuity for such a power. Okay, now you can ask, okay, but is it just for power bigger than 3? In fact, no, you can do it also for power p equals 3. And you remember that the power 3 was here, okay? Of course, you cannot take t to the power 3, but you have to change it. And this is, in fact, a microstructure that appears in micromagnetics. So this is called the cross-tie wall. So here, okay, the function is, I wrote it in theta. It's sinus theta, theta minus cos theta. So in theta equals 0, it's like theta to the third, okay? So here again, what you will do, so you want to create a microstructure that will beat this kind of jump. So here is much trickier because you will put a vortex here. So here you will turn like a vortex. And here you will decompose your jump in 2 jumps of 90 degrees, okay? So of course here you will have also some other jumps, but when you will look to these layers, you make your layer go to 0, so the energy of this will beat your energy of 1D. So this cannot be either a lower semi-continuous thing. So then the question is, okay, could you, how you can cook up a lower semi-continuous cost function? And here is, okay, so first of all, this is the most technical slide, so I will go quickly on this. So what do we mean by lower semi-continuous functional? So, so up to now, I said that if the configurations are BV, then we know that we have a jump set, okay? So there we can define, so if F is lower so it's continuous or something, then this quantity is well defined on the jump of M, okay? And for the other configurations that are L2, we just put plus infinity, and then we relax, okay? Relax the thing. So what's a relaxed functional is in fact the highest lower semi-continuous functional that stays below your functional, okay? So this is the definition. So it's in fact all the values that you can reach by going to BV configurations, okay, to the limit of this BV. And then we will say that the initial functional is lower semi-continuous if your functional coincides with the relaxed functional on the BV configuration. Okay, so that's the definition of lower semi-continuous. But you should really think to this. You cannot find the microstructure that decreases your energy of a direct jump energy. Okay. So now is how we can define such a cost function. So now I will speak about entropy. What do we mean by entropy? So the starting point is to look at the limit configuration. So all the limit configurations are with values in the unit circle, so 2D, with divergence free. So in fact, we saw that is an aconal equation, but we can see it also as a scalar conservation law. So how do we do it? So let us call U the first component. So since M is modulus 1, so the second component is 1 minus U squared. Okay, so this you can consider as a flux. Okay, and then what you will do is that the variables x, y of the plane, you can see it as a time variable and the space variable. Okay, so when you write divergence free, it's like taking the time derivative of u and then the space derivative of the flux. So this is a transport equation. Okay, so now you know that. So this flux, okay, it's not well defined. It's degenerate. Okay, so therefore we have to adapt such a theory. So the problem is that, okay, when you look to Cauchy problems associated to such a transport equation, nonlinear transport equation, in general, you don't have a unique solution. So therefore, the entropy solution concept was introduced. So let me recall how is this entropy solution introduced. So you need what is called entropy flux, which are two scalar functions that satisfy such a differential equation with respect to the flux. Okay? So then, if you consider that u is a smooth solution to this, then what you will do is that you multiply with eta prime u, and then you get that this quantity is 0. This quantity is called the entropy production. Okay? So if you have a smooth solution, so no shock, then of course the entropy production will not see anything. It's 0. Okay, so now, as I said, this is a problem because H is not smooth, so you have to adapt such an entropy concept to the diagonal equation. And that was done by this team, DKMO. So they said, okay, we will call entropy to the functional map that is defined in S1, which is in fact the target space of our vector fields, that will mimic this pair entropy flux, meaning that if you have a solution, a smooth solution to our equation, then the entropy production is 0. So exactly like this, right? So if u was a solution, then the entropy production, so that would be like phi of u here, is 0. Okay. So then you can say, okay, this is a nice definition, but we don't understand anything. So what's an entropy? Okay, so in fact there is a if and only if condition. So if you have here your circle, so entropy means nothing but taking a map from S1 with values in R2 such that the derivative, the angular derivative, stays tangent to Z. This is if and only if. And what is good is that this tells you that if you write this entropy in the frame Z perp, then an entropy is nothing. So if you know this component, then the second component should be the derivative of this. So like this, you can cook up a lot of entropies. So it's enough just to take a C infinity periodic function, you plug it here, you take the derivative of this, and this will be an entropy. So like this, you can have a lot of entropies, and this is good, because when you want to prove compactness or lower bounds, then you have things to play. Okay, and so what is so our aim was to construct good cost functions that lead to good candidates for the gamma limit of our energy. Okay, so what we will do? In fact, we will associate cost functions to subsets of entropies. Okay, so how do we will do this? So the main observation is that if you take a solution to our aconal equation, so that could have shocks, then the entropy production will be concentrated on shocks, and the density of this entropy production is nothing but the difference between the fluxes of the entropy along the shock. Okay, So of course, before the definition was that if M was smooth, then this is 0. So of course, if it's smooth, you don't have a jump set. Okay, so now is our idea. So it's like when, for example, when you want to construct a norm, you have to maximize something. So here the idea will be, so in order to construct a cost function, so you will fix a subset of entropies, okay? And then what you will do is that you will maximize the, this quantity, which is the entropy production density, among all the entropies in your set and among all the rotated jumps that you can have, right? Because you will fix the size of your jump, and then you will have such a configuration, such a jump configuration, and then you have to turn it. Because, in fact, the limit energy, you have this invariance by isometries, right? That depends just on the size of your jump, right? It will not tell you where you will have your jump. Okay, so that is the definition. So maximizing this entropy production density. And of course, okay, you cannot take arbitrary any subset of entropies, but you should have this symmetry. So the symmetry is important in order that you can, if you have the entropy phi, then you have minus phi. So this is always positive, right? Because our cost function should be positive. And you should also ask that once you have an entropy, then you have to have all the rotation entropies, because, as I said, we should have that these line energies are invariant by isometries. They will depend just on the size of the jump. Okay, so now you will say, okay, this is a nice formula, I don't understand anything. But you agree, okay. So I agree with you, so let me first tell you that, okay, once you will play with such a cost function, then you get that the energy is lower semi-continuous, so it's a good candidate. So you have that that relaxed energy touches this functional on BV configurations. And so what is more important is how you really construct practical examples. Okay, so the easiest thing is that when you consider your set of entropies, you will start from an entropy, then you rotate your entropy, and you look to the cost that you get. Okay, so and like this, you will hope to have some easy examples. Okay, so anyway, like this, so we will have a lot of examples to play. So okay, so we fix an entropy, we take all the rotations of that entropy and plus minus one. Okay, and then what I say is that the cost function generated by such a set of entropies is nothing but maximizing a convolution function. Okay, so the convolution, you see, it's a convolution with sinus of the function that gives you, in fact, the sine modulus of this guy. Okay, so already this is much easier, right? I mean, you just plug in here a function, and then you play with such a supremum. But then you can ask, okay, it's a supremum, so can't you give me some conditions on this function lambda in order that, for example, the maximum is achieved in 0? Because if it's in 0, then I will have that this cost function is nothing but the integral minus beta to beta of lambda theta sinus theta. Okay, so this is an easy formula. And yes, we can give such a configuration. So if lambda has such a convexity properties here, some symmetries, then this function is just this. Okay, so here you see that lambda is impaired, so it's the same what I wrote here. Okay, so for example, so such a function could be like minus sinus theta. So then you get to the first example. Okay, so you come back to our first example. So we already knew that that was the cost function as a gamma limit of the Ginzburg-Landau. So as a gamma limit, we already know that this is a lower semi-continuous thing. So we just rediscover it. okay, by playing with such a function lambda. Okay, then you can ask, okay, but can you play always just with one entropy? In fact, if you play just with one entropy, always this cost cannot be better than cubic. If you want to go to quadratic things, then you have to play with an infinite family of entropies. So for example, we proved that we can construct an infinite family of entropies in order to get to power 2. Okay? And in fact, this is something, so let me recall what's happening in scalar conservation laws. So in scalar conservation laws, when you look to small shocks, the entropy production is always cubic. So you cannot go to quadratic things. And what I forgot to stress here is that what is nice in this context is that this entropy production density is a measure that can change signs. So you know that when you define your entropies in the Khrushchev sense, you know that if you put your entropy to be convex or concave, you will have a sign on that measure. So here, this is what is nice. It's a larger concept, so you can have change of sign. So therefore, you can reach to so you can reach here to quadratic things. And in fact, it was the conjecture of Ambrosio that said that you can reach to every power between 1 and 3. Okay? So in fact, we gave an answer. A partial answer is that, okay, playing with those cost functions, we can always construct good lower semi-continuous functionals that are any power between 1 and 3, but just for jumps between 0 and pi over 4. Okay? In fact, okay, I think that, yeah, we can go also beyond this, so for the whole range of jumps, because for power 2 we succeeded to do it. But anyway, it's not written. Okay, so now you can ask me, okay, you did all this theory for what? So as I said, this gamma convergence method is a good method because like this, okay, you can get rid about one parameter. So say that you look to a good cost function where you will have the gamma convergence. So looking to the minimizers at the level epsilon is like, okay, you have always a good idea by looking to what's happening at the minimizer at level epsilon equals 0. So therefore, it's okay. You have to study this minimization problem under some boundary conditions. And of course, as I mentioned before, in order to get the existence of a minimizer, you need to have a compactness result. Okay. So this is done, but unfortunately, it's not done for the functional. This is an open question. So we don't know that this functional has a minimizer. What we know is that the relaxed functional will have a minimizer. So in some sense, the minimizer under some conditions, so for example, if you put powers between 1 and 3, it's okay. So, so we know that we will have a minimizer of the relaxed functional. This means that this minimizer is L2. So if we knew that this minimizer is BV, then it's good. We are done, because that would be also the minimizer of our initial one. But that's an open question, so we don't know that.
Sorry, I forgot. What is T here?
T means here. T here means the size of the jump.
Size of the jump.
Size of the jump. Yeah. So here you have. So your jumps are in general can be anything like this: C minus, C plus. Okay, and here is so it's like having here nu and C minus.
C positive means that it's always in one direction, or jump to the right always should be bigger than.
No, it doesn't matter, because T is nothing but the size.
Okay, good.
So therefore, I mean, you look into this energy, you don't know which jump you look. It's just that you know just the size of the jump. So that t goes from 0 to 2. Okay, so then, okay, I will. How am I doing? I have 5 more minutes.
You have 5 more minutes.
Okay, thank you. So as I said, okay, in general, the existence of a minimizer is open. But maybe we can say more if we take a stronger boundary condition. So a boundary conditions that will tell you that your configuration stays tangent here, but keep the same orientation, right? Because here the trickiest thing is that if you take just, if you know that just the normal component is 0, you could have also some boundary vortices appearing in your thing. So here you cannot have boundary vortices if you apply this. So here the natural candidate is, as I said, the solution to that aconal equation that comes from the distance function. Okay. So here, for example, you see that, okay, so the distance function, you know that, okay, you have characteristics given by the normal. So here you will see that the shock, right, is given by this singularity line. Okay, and so the conjecture was that if always you play with this kind of power between 1 and 3, and your domain is convex, then the viscosity solution, so this distance function, is the minimizer. Okay, so so let me give you an example. So we proved that, for example, if we have a stadium, so what is so particular to a stadium? So first of all, it's convex, but what is important is that if you look to the singleton, to the skeleton of the distance function, you have such a line, jump line, where the jump is constant. Okay, so this is very easy to deal with. So here we prove that if we take our cost functions, then the viscosity solution is a minimizer. So you can play also with some other convex domains, like an ellipse, or such 2 disks, for example, because also here the skeleton is a jump line that stays in the same direction. In fact, for example, it's should be an easy thing, but we cannot do it, for example, for a rectangle where we have 2 directions of the jump. Okay. So anyway, we have some examples where everything works, so the conjecture works. But in general, and now anyway, I'm not technical anymore. Now there will be just pictures, figures. We know that the convexity is very important. So what we will do is that we will cook up a universal, a non-convex domain where the viscosity solution, so that gradient perp of the distance function, is not a minimizer for every function, cost function that is not 0. That's the only thing. And that domain is this kind of how do you call this 4-leaf clover? Yeah, that's a lucky thing, right? It was yeah, it was lucky for us. So so that would be the universal domain. And then you can say, okay, but this kind of 4 disks, you have such a cusp coming in. So you can say, okay, can you cook up also smooth domains? And yes, we can, but those domains are not universal. So that works for if you fix your cost function, then you will cook up such a smooth domain. Okay, so let us go. So these are very nice pictures. So Benoit Merlet did it. So this is the domain, and so we will look to the gradient of the distance function. So at the boundary we will stay tangent. Okay, and so you see that here you will have something like a vortex. Here you will have also something like a vortex. But what will happen is that these are line singularities because on a point like here, you are at the equal distance from here and to here, right? So if you look to the jumps coming here, you will have like a 100-degree jump here, and over here you will have like a 90-degree jump. Okay, so this is the viscosity solution, and then you will say, okay, but you said that this is not a minimizer, so how you will cook your counter candidate? And this is all this theory. So in this theory, vortices cost 0 energy. So you can play with vortices. Okay, so the counter candidate is to consider that here you have vortices. Okay, so if you put here a vortex, then it's okay for the boundary, so you stay tangent. Okay, and now what's happening is that the line singularities appear here. Okay, because right here you will turn like this, here you will turn on the other side. So those are nothing but these jumps. Okay, I will finish. So this is, you see that in fact these two lines have less perimeter than smaller length than this one. So therefore, in fact, you can compute and you will have that the energy of this counter candidate is strictly smaller than the viscosity one. Okay, and how you will construct the smooth domain? What you will do is that you will put yourself like epsilon distance in the interior. Okay, so before the cusp was here, like this. Okay. So then, of course, since it's a distance function and you just put your domain inside, you will have the same configuration as before. And now, if you put your vortex here, you will have a slightly problem here because here you are not tangent. So if you make a zoom, you will see that this will not stay tangent. So in this kind of region of order epsilon, you have to move to change a little bit your configuration. So you have to stay tangent here. Okay. So your flux will go like this. So of course you have to put something back in order that the divergence is free. And okay, plugging in such a distorted configuration, anyway, you will change that at the small epsilon domain. So you will still get that the energy of this configuration is smaller than the energy of the viscosity solution. So thank you very much.
So my question is from the class of, so you did all this theory, and now if you compare with physics literature, there are many models of domain walls in magnetics, for example.
Yeah.
So if you compare your results with the physics results, with the theoretical physics results on nail wall or block wall with point defects and without defects, so what is the advantage of your approach in the sense of predicting the configuration of magnetization in space?
Okay, so first of all is that, so as you see in the end, there are some configurations where I could say that, okay, that viscosity solution, what is called in micromagnetics the Landau state, that would be the ground state energy state. Yeah, so that's the ground state. Or, for example, if you give me such a, okay, anyway, they will never think to create such a 4-leaf clover domain. I could say, okay, it's not the distance, so not that Landau state that will give the ground state of the energy. That would be one. So second is, so of course, okay, that's really for an analysis that I played around with the potential that can be any power between 1 and 3. So of course that term in physics is like the anisotropy. So physicists in anisotropy, they consider that are like, you make like a Taylor expansion, And in fact, due to some symmetry, you will not have the odd term. So it can be m3 to the power 2, m3 to the power 4, and so on. Right. So you cannot have such a thing. So of course, this is more like well, pure mathematics things, because I mean, I think it's very interesting that okay, we have we can make a classification that if the cost function is with the power bigger than 3, then okay, you have microstructure coming in, and so I don't know if a physicist care about such a thing, but me as an analyst, I like it. Yes.
If the vortex energy is 0, why not to produce many vortices? Why configuration define number of vortices? It costs nothing to produce infinite.
Right. So okay, I mean, as I said, the energy is 0, but so for example, if you take if your domain is the ball, okay, and you consider this boundary condition. So of course, the Landau state, so that distance function is nothing but this vortex. But of course, so the energy is 0, but the vortex is there. I mean, so this is really so m0 is x squared over modulus of x. So the vortex is there, but I mean, it costs 0 energy, because this energy you really need to put. So it's like putting vortices, like you fill in. You should fill in a line in order that the energy is not 0, right? I mean, that's why the energies really should see something of codimension 1 in this model.
I wonder whether any of this can be extended to 3D. I mean, I know that's an unfair question, but
yeah, no. That's a very good question. In fact, okay. So so first of all, so the big so the answer would be almost nothing is known in 3D. So for example, in 3D, the energy that is cubic, you can show in 3D that you have a microstructure coming in. So the cubic energy cannot be a gamma limit. So that was done by Delelis, for example. And in fact, okay, we discussed, and I think it's working for every power. Okay, what you can do in 3D, so that doesn't rule out the compactness result. So always when you should think to 3D, is not the divergence constraint that you should put, but the curl-free constraint in order to have a gradient field. Okay, and if you want to adapt this method of entropy of entropies, so when you will look to the system of scalar conservation laws associated to the aconal equation, unfortunately, all the entropies are trivial. So you cannot play around with subsets of entropies. So some other method should be adopted.
Can you repeat again what was the role of the cross-tie wall example?
Okay, so the cross-tie wall was that right here. So that if you take this energy, so this cost function, then this will not lead to a lower semi-continuous functional, right? Okay. So this is why, because in fact this is the good energy of a cross-tie wall, but up to the angle pi over 4. Because okay, I didn't say, but such a configuration is not just for 180 degree. In fact, it works up to the angle pi over 4. And how do you will do it? You should imagine that on this point, what you will do with your system of layers, you will pull it. So like this, you will have, so at the beginning you are like this, and then you will pull it here. So you will go like this. So here, when you will look to what's happening here, this is like an angle of pi over 4. So that's the most you can get. And the effect, so what's happening is that after pi over 4, you have to change this energy. So you have to convexify it as a okay. In fact, it's exactly this function, but you should take it linear here. So that will give you the right entropy to play in order to get the right cross-tie wall. Yeah, anyway, I'm here for the week, so you can.